Recently, NASA released new images of the interstellar object 3I Atlas, and buried in that gallery is something that shouldn't exist. One of those images shows a plume extending from this cosmic visitor in a direction that defies everything we understand about how objects behave in space. This isn't a measurement error or a calibration issue. This is a high-resolution photograph captured by one of the most advanced cameras ever sent beyond Earth, and what it reveals is physically impossible according to conventional comet science. Let me be clear about what we're looking at here. On October 2nd, 2025, the HiRISE camera aboard NASA's Mars Reconnaissance Orbiter turned away from its usual task of photographing the Martian surface and pointed into deep space. The target was 3I Atlas, the interstellar comet that's been travelling through our solar system, and what HiRISE captured in that moment has scientists asking questions they didn't expect to be asking. The image shows a distinct plume of material streaming away from the nucleus, extending thousands upon thousands of kilometres into space. That part isn't unusual. Comets develop plumes and tails. That's what comets do. But this plume is pointing in the wrong direction. Not just slightly off, not within some margin of error we can explain away with orbital mechanics or viewing angle corrections. Wrong in a way that violates the fundamental physics of how solar radiation, solar wind, and thermal processes interact with icy bodies in space. Stay with me, because in the next several minutes we're going to walk through exactly why this image represents something unprecedented, what conventional explanations have been considered, and why they fail, what experts like Harvard astrophysicist Avi Loeb are saying about the implications, and what observations are coming in the weeks ahead that might finally give us answers to a mystery that's growing more complex with every new piece of data we collect. When you look at the HiRISE image for the first time, you might not immediately see what's wrong. It looks like a comet. There's a bright central nucleus, a diffuse cloud of material surrounding it called the coma, and that elongated plume stretching off to one side. Your brain recognizes the pattern. Comet. Check. Move on. But the scientists who analyzed this image didn't move on, because they know something you might not consciously think about when you see a comet photograph. Direction matters. The direction a plume points tells you what's causing it. Sunlight heats ice, ice turns to gas, gas carries dust particles, and that stream of material gets pushed around by radiation pressure and solar wind. There are rules. Physics doesn't care about mystery or drama, it follows laws. And according to those laws, the plume in this image is pointing where it has no business pointing. Let me paint the geometry for you, because geometry is where this whole thing falls apart. When HiRISE captured this image, 3I Atlas was on a specific trajectory through our solar system. We know its path, we know its speed, we know where the sun was relative to its position, and we know which direction it was moving. Those aren't guesses, those are tracked, measured, confirmed coordinates. The plume in the image extends roughly perpendicular to the direction toward the sun, not away from the sun, where you'd expect solar radiation to push material, not toward the sun, where you might see some unusual jet activity from ice pockets on the sunward side. Perpendicular, at a right angle to the solar direction. And here's the part that makes it worse. The plume also appears to extend in the direction the object is moving, ahead of it, leading its trajectory through space. Think about that for a second. This object is hurtling through our solar system at tremendous velocity, and there's a stream of material pointing ahead of where it's going. If you threw a ball and saw dust trailing in front of the ball's path instead of behind it, you'd know something was interfering with normal physics. You'd know some force was acting on that dust that doesn't fit the throw itself. That's what we're seeing here, except instead of a ball, it's a comet-like object from interstellar space, and instead of a simple throw, we're dealing with the complex gravitational and radiative environment of our solar system. The forces at play should be predictable. Solar gravity, solar radiation pressure, solar wind, the object's own velocity, and any outgassing from its surface. We can model all of that. We do model all of that. And none of those models produce a plume geometry like what HiRISE photographed. Avi Loeb, the Harvard astrophysicist who's been following 3I Atlas closely since its discovery, published an analysis of this image that gets straight to the uncomfortable question. If the plume direction can't be explained by natural comet processes, what does explain it? He doesn't jump to conclusions. He doesn't claim proof of anything extraordinary. But he does what good scientists do when data doesn't fit expectations. He asks whether we're looking at something other than a natural object behaving according to natural processes. He asks whether this could be a technological signature. And before you dismiss that as sensationalism or attention-seeking, understand that this question comes after methodically working through conventional explanations and finding them insufficient. This isn't the first hypothesis. It's the hypothesis you arrive at when the first dozen hypotheses fail to account for what you're observing. The high-rise camera isn't some hobbyist telescope, producing grainy, ambiguous images that could be interpreted 6 different ways depending on your biases. This is a military-grade reconnaissance camera that was built to spot details on the Martian surface from orbit. It can resolve features smaller than a dining room table from hundreds of kilometers above Mars. When it turns, the capability toward a deep space target, even 1 millions of kilometers away, it produces images with clarity that ground-based telescopes simply cannot match from Earth's distance. The October 2nd observation caught 3I Atlas at a point in its trajectory when it was significantly closer to Mars than to Earth, which gave HiRISE an advantageous viewing angle and proximity that Hubble and other Earth-based instruments couldn't replicate. This wasn't a lucky snapshot. This was a carefully planned observation during a narrow window of optimal positioning, and the data it returned is unambiguous about what's physically there in space. A plume in the wrong direction. What makes this particularly disturbing for scientists who study comets is that we have previous images of 3I Atlas from when it was farther out in the solar system, approaching from interstellar space. Hubble captured it multiple times during that inbound phase of its trajectory. Those earlier images showed plume activity, but the orientation was different. When the comet was heading more directly toward the Sun from a greater distance, the plume behavior appeared more consistent with solar-driven processes. You could look at those Hubble images and think, okay, ice is sublimating from solar heating, radiation pressure is pushing material away. This looks like a comet doing comet things. But as 3I Atlas got closer and its trajectory bent around the Sun, and especially now in this high-rise image taken from Mars's vantage point, the plume geometry has shifted into something that doesn't fit that narrative anymore. It's as if the object changed its behavior, or as if we're finally seeing it clearly enough to recognize that it was never behaving conventionally in the first place. The scale of this plume adds another layer of strangeness. We're not talking about a little puff of gas or a thin jet barely visible against the background stars. The plume extends across a distance that would span significant fractions of the space between Earth and Moon if you could somehow transplant it into our local neighborhood. The massive material in that plume, the energy required to eject it from the nucleus and send it streaming in that direction, the sustained activity over the time period it must have taken to form that structure. All of that requires mechanisms that generate force and motion, and those mechanisms have to be powered by something. In normal comets, that power source is the Sun. Solar radiation provides the energy that heats ice, creates gas pressure, and drives material off the surface. But if the plume is pointing perpendicular to the Sun, and forward along the direction of motion, where is the energy coming from? What's doing the pushing, and why is it pushing in that specific direction? There's a reflexive urge to come up with easy answers. Maybe there's a vent on the nucleus that happens to be oriented that way. Maybe the object is rotating and that's creating some kind of directional bias in how material escapes. Maybe there's an ice pocket that got exposed and it's more volatile than the surrounding surface, so it's outgassing more vigorously in one direction. All of those are reasonable guesses. Scientists have been considering exactly those possibilities. But when you work through the math, when you calculate thermal speeds and radiation pressure effects and solar wind drag, when you account for the observed velocity of the plume material and the direction it's travelling relative to the nucleus and the Sun, those easy answers don't hold up. They predict plume geometries that look different from what we're seeing. They predict behaviours that should evolve over time in ways we aren't observing. They require conditions that would produce other signatures we should be detecting, but aren't. This is what makes the high-rise image so valuable and so troubling at the same time. It's valuable because it provides a clear, high-resolution view of 3I Atlas from a unique angle, at a critical point in its trajectory. It's troubling because that clarity and that angle reveal something that shouldn't be there, according to our understanding of comet physics. If this were a fuzzy image from a distant telescope, we could say maybe it's an artifact, maybe it's a viewing angle illusion, maybe we need better data. But this is better data. This is some of the best observational data we're going to get of this object during its passage through our solar system, and it's telling us that something doesn't fit. That's not a failure of observation. That's the observation succeeding in showing us reality, and reality is handing us a puzzle we don't know how to solve with the tools we've been using. So here we are, staring at an image from NASA's Mars Reconnaissance Orbiter, looking at a plume from an interstellar visitor, and confronting the fact that the plume is pointing in a direction that breaks the rules we thought governed these objects. We can ignore it. We can assume there's some conventional explanation we just haven't thought of yet. Or we can take the data seriously and follow it wherever it leads, even if that means asking uncomfortable questions about what we're actually looking at. Drop a comment and tell me what direction you think this plume should be pointing, because what we're seeing doesn't make sense, and understanding why it doesn't make sense is the first step toward figuring out what's really happening up there in the space between stars. Before we can understand why this plume direction is impossible, we need to establish what normal looks like, because if you don't know how comets are supposed to behave, you can't appreciate how bizarre this image actually is. Comets are among the most predictable objects in our solar system once you understand the forces acting on them. They're not mysterious, they're not erratic, they follow physics just like everything else, and the physics of comets is pretty straightforward. A comet is essentially a dirty snowball, a mixture of ice and rock and dust that spent billions of years frozen in the outer reaches of the solar system or beyond. When one of these frozen bodies gets nudged into a trajectory that brings it closer to the sun, something inevitable happens. Heat. The sun radiates energy in all directions, and when that energy hits a comet's icy surface, it doesn't just warm it up. It causes sublimation, which is the process where ice transforms directly from solid to gas without passing through a liquid phase. You've seen this if you've ever watched dry ice fog machines at a concert or Halloween display. Dry ice is frozen carbon dioxide, and when it warms up, it doesn't melt into liquid CO2. It turns directly into gas, creating that dramatic fog effect. Comet ice does the same thing, except instead of carbon dioxide in a fog machine, you're dealing with water ice, carbon monoxide ice, carbon dioxide ice, methane ice, and a mix of other volatile compounds frozen onto and into the nucleus. As the sun's energy reaches the comet and those ices start sublimating, gas molecules escape from the surface carrying dust particles with them. That expanding cloud of gas and dust is what creates the coma, the fuzzy atmosphere around the nucleus, and as more material gets released, some of it streams away from the comet in the characteristic tail. Here's the key part, the part that defines normal comet behavior. The direction of that streaming material is controlled by two main forces: solar radiation pressure and solar wind. Solar radiation pressure is exactly what it sounds like. Photons from the sun carry momentum, and when they hit dust particles in the comet's coma, they transfer that momentum, pushing the particles. Since the photons are coming from the sun, they push the dust away from the sun. That creates what's called the dust tail, and it always points away from the sun regardless of which direction the comet itself is moving. You could have a comet heading toward the sun, or away from the sun, or across the sun's path, and the dust tail would always point away from the sun. Solar radiation doesn't care about the comet's motion, it cares about where the sun is. The second force, solar wind, affects the gas molecules in the coma. Solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the sun at high speeds. When those charged particles interact with the ionized gas molecules around the comet, they drag them along, creating what's called the ion tail or plasma tail. Just like the dust tail, the ion tail points away from the sun because the solar wind is flowing away from the sun. So a typical comet develops two tails during its approach to the sun and passage through the inner solar system. Both tails point away from the sun. One is made of dust, slightly curved because the dust particles are heavier and take longer to respond to radiation pressure. The other is made of ionized gas, straighter and more directly antisolar because the gas responds more immediately to the solar wind. That's the textbook picture. That's what comets do. They sublimate on the sunward side, material escapes, and radiation pressure and solar wind push that material away from the sun. Now let's talk about what happens to material that gets ejected from the comet's surface before radiation pressure and solar wind have a chance to act on it. When ice sublimating from the nucleus turns to gas, those gas molecules are moving. They have thermal velocity, the speed they move at based on their temperature. For the kinds of molecules we find in comets, water vapor, CO, CO2, that thermal velocity is relatively modest. We're talking speeds comparable to a few hundred meters per second, not thousands of kilometers per hour. As the gas expands away from the nucleus, it carries dust with it. But that dust is heavy compared to gas molecules, so it doesn't get accelerated to high speeds. It drifts outward relatively slowly. If nothing else acted on that material, if there were no solar radiation and no solar wind, the gas and dust would just expand radially away from the nucleus in all directions based on where the sublimation is happening on the surface. A patch of ice on the sunward side sublimates. Material flows outward from that patch. A patch on the shadowed side, if it's warm enough, also sublimates, and material flows outward from there too. But in reality, radiation pressure and solar wind dominate pretty quickly once the material gets any distance from the nucleus. Within a relatively short distance, thousands of kilometers from the comet, the dust particles start getting pushed preferentially in the anti-solar direction. The gas gets swept up by solar wind, also pushed anti-solar. So even if you have jets pointing in various directions close to the nucleus because of active vents or rotating surface features, by the time you're looking at structures that extend tens of thousands or hundreds of thousands of kilometers, those structures are aligned with the anti-solar direction. That's the rule. That's what decades of comet observations have confirmed. Material ends up pointing away from the sun. There's one more aspect to normal comet behavior that's important here. As a comet moves through space, it's also moving through the environment of solar wind and radiation. If the comet is heading away from the sun, after passing perihelion, its closest approach, the tail extends behind it in the sense that the tail points away from the sun. But because the comet is also moving away, the tail kind of trails behind. If the comet is heading toward the sun on its inbound trajectory, the tail still points away from the sun, which means the tail is actually streaming out ahead of the comet's direction of motion. Picture a car driving in reverse with a flag on the front. The flag points backward relative to the car's forward direction, but backward. In that case means the direction the car came from, not the direction it's going. Comets are like that. The tail direction is set by the sun, not by the comet's velocity through space. So when we talk about normal comet behavior, we're talking about plumes and tails that follow very specific rules. Sunward heating drives sublimation. Material escapes from the areas being heated most intensely, and then radiation pressure and solar wind push that material into an anti-solar configuration. If you see a plume or tail pointing toward the sun, that's weird, but it's explainable if there's a vent on the night side that happens to be outgassing, and you're catching it before solar wind has redirected the material. If you see a plume pointing perpendicular to the sun direction, that's stranger, but maybe you're looking at a jet from a specific vent, and the viewing angle makes it look perpendicular when it's actually got some component in the anti-solar direction that's not obvious from your perspective. If you see a plume pointing ahead of the comet's direction of motion, and that direction is perpendicular to the sun, now you're in territory where normal explanations start running out. Because here's the thing, for a plume to point ahead of a comet's motion, it means material is being ejected forward faster than the comet itself is moving, or material is being acted upon by a force that's pushing it forward. Thermal velocities from sublimation aren't fast enough to create sustained forward plumes unless the comet is moving incredibly slowly, which 3I Atlas is not. Radiation pressure pushes away from the sun, not forward. Solar wind drags anti-solar, not forward. Gravitational interactions with the sun or planets would pull material toward those bodies, not ahead of the comet's path. There isn't a natural force in the standard model of comet physics that puts material in front of where the object is going, especially when that forward direction is perpendicular to the sun. Every mechanism we know about either pushes material sunward because it's still bound to the nucleus and being pulled by the nucleus's gravity and the sun's gravity, or it pushes material anti-sunward because radiation and wind take over. Forward and perpendicular to the sun. That requires something else, and that's why the high-res image is so disruptive. It shows exactly that configuration, a plume extending in the direction of motion, roughly perpendicular to the solar direction. It's not a subtle deviation that could be explained by measurement uncertainty. It's an obvious geometric feature that anyone analysing the image can see and measure. The scientists who work on comets for a living, who've spent careers studying sublimation rates and dust dynamics and plasma interactions, they see this image and they know it doesn't fit. They can try to propose scenarios that might produce something sort of like it if you make specific assumptions about nucleus shape or rotation or vent, locations or material properties. But when you work through those scenarios in detail, they either fail to reproduce the observed geometry, or they require conditions so specific and unlikely that you're left wondering if you're forcing a square peg into a round hole just to avoid the uncomfortable implication that maybe this isn't a normal comet behaving abnormally. Maybe it's not a normal comet at all. That's the foundation we need to understand. Normal comets create plumes and tails that point away from the sun because that's where radiation pressure and solar wind push material. Normal comets don't create sustained forward-pointing plumes perpendicular to the solar direction because there's no force in the natural environment that does that. And yet here's 3I Atlas, an object we've been calling a comet because it looked comet-like when we first detected it, showing us a plume that violates those basic expectations. And now we're confronted with the possibility that our assumptions about what this object is and how it behaves might be fundamentally wrong from the start. So with that understanding of what comets are supposed to do, let's look more carefully at what 3I Atlas is actually doing, and why that plume direction isn't just unusual, but physically impossible according to conventional comet science. When scientists first analysed the HiRISE image, they did what scientists always do. They measured, they calculated angles, they determined where the sun was relative to 3I Atlas at the moment of observation. They figured out the object's velocity vector, which direction it was moving through space. They mapped the orientation of the plume relative to both the solar direction and the motion direction, and the measurements came back clear. The plume extends in a direction that cannot be explained by conventional comet physics. Not sort of can't be explained if you squint and make generous assumptions. Can't be explained. Period. Full stop. Avi Loeb's analysis of this image gets into the specifics in a way that removes any wiggle room for ambiguity. The plume is not pointing toward the sun, is not pointing away from the sun, it's pointing at an angle roughly perpendicular to the Sun-Comet line. And critically, it's pointing in the direction that 3I Atlas is travelling, ahead of the nucleus along its trajectory. Imagine you're driving a car and you release a cloud of smoke from the front bumper that travels forward faster than your car is moving. That's essentially what we're seeing, material streaming ahead of the object. And the question that immediately jumps out is, what mechanism ejects material forward? What pushes it in that direction? What sustains it over the scale we're observing, which is not a small localized jet but a plume structure extending across distances that would take conventional comet material hours or days to traverse at thermal speeds? Let's be precise about what forward means here, because trajectory, geometry in space can get confusing. 3I Atlas entered our solar system from interstellar space, passed relatively near the Sun though not as close as typical comets, and is now heading back out toward interstellar space on a hyperbolic trajectory. At the time of the HiRISE observation, the object was on the outbound leg of that trajectory, moving away from the Sun and away from the inner solar system. Its velocity vector pointed away from the Sun, but not directly. It was travelling at an angle, moving both away from the Sun and perpendicular to the radial line between Sun and object. The plume in the image extends ahead of the nucleus along that velocity vector, not perpendicular to the velocity, not trailing behind, ahead, in the direction the object is going. Now, you might think, okay, maybe there's a vent on the leading hemisphere of the nucleus that's ejecting material forward, and we just happen to be catching it at the right moment before radiation pressure turns it around. That's a reasonable first thought, but it doesn't survive scrutiny. For a vent to create a forward plume that extends as far as what we're seeing in the HiRISE image, the material would need to be ejected at speeds significantly higher than typical thermal velocities for comet volatiles. Water vapour sublimating from ice moves at speeds around a few hundred meters per second. That's fast in everyday terms, but slow when you're talking about creating structures that extend thousands of kilometers over relatively short time periods. If material is being ejected at thermal speeds, it expands outward, yes, but it also gets acted upon almost immediately by other forces. Solar radiation starts pushing it. Solar wind starts dragging it. Within a short distance from the nucleus, those external forces dominate over the initial ejection velocity, and the material's direction shifts toward antisolar. For material to maintain a forward direction over the scales we're seeing, either it's being ejected at velocities much higher than thermal, which would require some mechanism to accelerate it beyond what sublimation pressure can achieve, or it's being continuously pushed or maintained in that direction by an ongoing force. Neither of those things happens in normal comets. Normal comets don't have mechanisms to accelerate material to high velocities beyond thermal speeds, unless you're talking about very specific and rare events, like explosive release of subsurface pressure, and even then, the material goes in whatever direction the vent happens to point, which is usually related to where solar heating is causing the pressure buildup, meaning sunward or near sunward. They don't have mechanisms to continuously push material forward against the dominating influence of solar radiation and solar wind. Loeb's analysis points out another critical detail. Previous Hubble observations of 3I Atlas when it was farther from the Sun and on its inbound trajectory showed Plume activity, but the orientation was different. At that earlier phase, the Plume appeared more aligned with what you'd expect from solar-driven processes. Material streaming in directions that could be reasonably attributed to sunward heating and anti-solar radiation pressure. But as the object got closer to the Sun, swung around, and began its outbound journey, the Plume geometry changed. The high-rise image taken when 3I Atlas was closer to Mars than Earth and observed from that advantageous angle reveals the Plume in this perpendicular forward configuration that wasn't as obvious, or perhaps wasn't present in the earlier observations. That evolution is significant. If the Plume orientation has changed over time, it suggests that whatever is causing it isn't a static feature like a fixed vent pointing in a certain direction. It suggests that the process creating the Plume is responsive to the object's changing position and velocity relative to the Sun. In normal comets, that kind of responsiveness makes sense because the process is driven by solar heating, which changes as the comet's distance from the Sun changes and as different parts of the nucleus get illuminated due to rotation. But in normal comets, that responsiveness produces predictable Plume orientations. Sunward heating, anti-solar tails. The responsiveness we're seeing in 3I Atlas produces something else. A Plume that shifts into a configuration that shouldn't exist according to natural comet processes. Let's talk about scale again because it's easy to gloss over how big this Plume is. We're not looking at a faint whisper of gas barely visible above background noise. We're looking at a structure that extends across distances comparable to the space between planets in the inner solar system. The mass of material in that Plume, the total amount of dust and gas that's been ejected and is now suspended in space, in that configuration, represents a significant fraction of what the nucleus is capable of producing. For context, typical comet nuclei are a few kilometers across. They're small, they're fragile, they don't have enormous reservoirs of volatile material that can sustain massive outgassing indefinitely. Every kilogram of ice that sublimates and turns to gas represents material that's gone from the nucleus forever, either blown away by solar wind or gravitationally unbound and drifting through space. A Plume of the size we're seeing in the high-rise image represents substantial mass loss, and that mass loss is happening in a direction that requires energy and mechanisms beyond what solar heating alone can provide. Think about the geometry one more time. Perpendicular to the Sun means the area of the nucleus that's producing this Plume isn't the area receiving maximum solar heating. The sunward side of the nucleus gets the most energy. That's where you'd expect the most vigorous sublimation. But the Plume isn't coming from the sunward side. It's coming from somewhere else, from a region that's receiving less direct solar energy, and yet it's producing a Plume that rivals or exceeds what you'd expect from the sunward side. That inverted relationship between energy input and material output is another red flag. It's another piece of evidence that whatever's driving this Plume isn't primarily solar heating. Something else is providing the energy to volatilize ice, accelerate material, and sustain the Plume in that specific direction. Avi Loeb, in his characteristic straightforward style, asked the question that needs to be asked even though it makes people uncomfortable. Could this be a technological signature? Could we be looking at a Plume produced not by natural sublimation, but by some kind of propulsion system or debris clearing mechanism or other technology? Before you roll your eyes or dismiss that as science fiction, consider the logic. We've ruled out solar heating as the primary driver because the Plume direction doesn't match. We've ruled out radiation pressure and solar wind because they push anti-solar, not forward perpendicular. We've ruled out thermal velocities as insufficient to sustain forward motion over these scales. We've noted that the Plume orientation has changed over time in ways that don't fit passive rotation or fixed vent geometry. We're left with a gap, a space where conventional explanations should be, but aren't. And when you have a gap like that, you have two choices. You can throw up your hands and say, we don't know, it's a mystery. Maybe future observations will clarify. Or you can hypothesize. You can propose mechanisms that might fill the gap and test those hypotheses against the data. A technological mechanism isn't the first hypothesis. It's not even the second or third. It's the hypothesis you consider after the natural mechanisms fail. And in this case, they have failed. Not because scientists aren't creative enough or haven't thought hard enough about exotic comet behavior. They've thought very hard. They've run models. They've compared 3i Atlas to every weird comet we've ever observed. And none of the natural explanations produce what we're seeing. So Loeb asks, what if this object is clearing a path? What if it's ejecting material ahead of its trajectory to sweep away micrometeoroids or dust particles that could damage sensitive components during high-velocity transit through space? What if the plume is a byproduct of propulsion, material being expelled to generate thrust, and the direction makes sense because the object is accelerating or adjusting its course? What if we're looking at something that's not a comet at all, something that's using comet-like camouflage of ice and dust, but fundamentally operating on principles that are technological rather than geological? Those are uncomfortable questions. They challenge our assumptions about what's natural and what's artificial in deep space. They open doors to speculations that verge on the taboo in professional astronomy because claiming something might be artificial technology without ironclad proof is a career-limiting move. But Loeb isn't claiming proof. He's saying the data doesn't fit natural explanations, and therefore we need to consider alternatives, including alternatives that involve technology. That's not sensationalism. That's intellectual honesty. That's following the evidence even when it leads somewhere unexpected. The high-rise image doesn't prove anything about technology. It proves that 3i Atlas has a plume pointing in a direction that conventional comet physics can't explain. That's the fact. The interpretation of that fact is where things get speculative. Maybe there's a natural mechanism we haven't thought of yet. Some exotic configuration of nuclear structure or volatile composition or radiation environment that produces forward perpendicular plumes in specific circumstances. Maybe 3i Atlas just happens to be the first object we've observed closely enough to see that mechanism in action. Or maybe the plume is telling us something more fundamental, that our classification of this object as a comet was wrong from the beginning, and we're looking at something that requires a different framework to understand. Either way, the plume direction breaks the rules. That's not in dispute. What caused the breakage is the question we're now forced to confront. And here's what makes this moment so critical. We're not going to be left wondering indefinitely. 3i Atlas is still observable. It's still within range of our best telescopes and instruments. In the coming weeks, targeted observations from Hubble, from James Webb, from large ground-based observatories, will gather data that can distinguish between natural and technological hypotheses. Spectroscopy will tell us what the plume is made of, whether it's ordinary water and carbon compounds or something more unusual. Infrared observations will reveal thermal signatures, whether the nucleus is being heated by the sun or by something internal. High-resolution imaging will track how the plume evolves, whether it fades as solar influence decreases or persists in ways that suggest ongoing activity independent of solar energy. The answers are coming. But right now, in this moment, we're staring at an image that challenges our understanding, and that challenge demands we take it seriously. What makes the high-rise image so powerful, beyond just the plume itself, is where it came from and why it was possible to capture in the first place. Because the Mars vantage point gave us something we couldn't get from Earth. There's a reason the high-rise observation matters more than just being another image in a growing collection. That reason is geometry, specifically the geometry of where Mars was relative to 3i Atlas on October 2nd, 2025, and what that positioning allowed scientists to see that would have been impossible or much less clear from Earth-based telescopes. Orbital mechanics played into our hands, creating a narrow window, where Mars Reconnaissance Orbiter could point its high-resolution camera at this interstellar visitor and capture details that observatories on Earth simply couldn't match. Not because Earth's telescopes aren't capable, but because distance and angle matter enormously when you're trying to resolve structure on an object millions of kilometers away. Let's talk about what high-rise is, because understanding the camera itself helps you appreciate why its image of 3i Atlas is such a big deal. HIRIS stands for High Resolution Imaging Science Experiment, and it was designed for one primary purpose, mapping the Martian surface in exquisite detail to identify potential landing sites for rovers and study Martian geology at scales that reveal individual rocks and small-scale features. The camera's resolution is extraordinary. From its orbital altitude above Mars, it can distinguish objects less than a meter across. That's not just impressive. That's functionally a spy satellite pointed at another planet. The optics, the sensors, the image processing algorithms, All of it was engineered to extract maximum information from reflected sunlight off Martian terrain. But HiRISE wasn't locked into only photographing Mars. The spacecraft it's mounted on, Mars Reconnaissance Orbiter, has the ability to pivot and point the camera in different directions, and mission planners occasionally use that capability for special observations. Imaging Phobos, one of Mars's moons, capturing Earth and our moon from Mars's perspective, and now turning toward deep space to photograph an interstellar object during a rare alignment. That alignment is what made October 2nd significant. On that date, 3i Atlas was much closer to Mars than to Earth. Not close in the sense of being nearby, we're still talking about distances measured in millions of kilometers, but close enough that HiRISE's powerful optics could resolve the nucleus and plume structure far better than telescopes on Earth could at that same moment. Distance matters in astronomy, in ways that aren't always intuitive. You might think, well, Hubble is more powerful than HiRISE, so Hubble should be able to see 3i Atlas better, regardless of where it is. And yes, Hubble is an incredible instrument, but Hubble is in Earth orbit, and Earth was farther from 3i Atlas than Mars was during that October observation. The extra distance means the object appears smaller in Hubble's field of view. Smaller apparent size means fewer pixels on the object. Fewer pixels means less detail. You can still see the object, you can still measure its brightness and general shape, but resolving fine structure like the orientation and extent of a plume becomes harder. HiRISE, being closer via Mars's position, got a better view. More photons from the object reached the camera per unit area. The plume structure filled more of the sensor's field, and the resulting image had the clarity needed to unambiguously show that perpendicular forward, plume geometry. But proximity wasn't the only advantage. Viewing angle mattered just as much. When you observe an object from a single location, you're seeing it from one perspective. You can learn a lot from that perspective, but you're also limited by it. If a plume is pointing partially toward you or away from you, foreshortening effects make it hard to judge its true direction in three-dimensional space. You might think it's pointing in one direction, when actually it's pointing in a slightly different direction that's just aligned with your line of sight. This is where triangulation becomes powerful. By observing the same object from two different locations, Earth and Mars, you get two different perspectives, and combining those perspectives allows you to reconstruct the object's three-dimensional structure and motion far more accurately. The October 2nd observation from Mars Reconnaissance Orbiter provided exactly that second perspective. Earth-based telescopes had been tracking 3i Atlas for months, gathering data on its position, brightness, and general activity. Those observations established a baseline. Then HiRISE added a data point from a completely different angle, from a vantage point separated from Earth by the distance between our planet and Mars, which at that time was significant. That separation meant the angle between Earth's line of sight to 3i Atlas and Mars's line of sight to 3. I-Atlas was large enough to matter. Triangulation using those two lines of sight allowed researchers to refine the object's trajectory with much higher precision than was possible from Earth observations alone. Reports suggest the trajectory accuracy improved by roughly tenfold, meaning uncertainties in where the object was and where it was going shrank dramatically. Why does trajectory accuracy matter for understanding the plume? Because you need to know precisely which direction the object is moving to determine whether the plume is leading or trailing or perpendicular or some combination. If your trajectory has uncertainty, your interpretation of plume geometry has uncertainty. Tighten the trajectory, and suddenly the plume's orientation becomes unambiguous. That's what the Mars observation did. It removed wiggle room. It confirmed that yes, the plume is pointing ahead of the object's motion, and no, that's not a viewing angle illusion or a measurement artifact. It's real. It's there in three-dimensional space, and it's pointing where it shouldn't be pointing. There's another aspect to the Mars observation that's worth appreciating. Pointing HiRISE at a deep space target isn't trivial. The camera was built to photograph a planet that fills a substantial portion of the sky from orbital altitude. Pointing it at a tiny distant object requires precise navigation, careful timing, and acceptance of the fact that you're dedicating expensive operational time to something other than the primary mission. Mars Reconnaissance Orbiter is a spacecraft. It has a schedule. It has ongoing science objectives related to Mars. Taking time to swivel the camera and point it into deep space means delaying or skipping other planned observations. Mission planners don't do that lightly. The fact that they chose to do it for 3i Atlas tells you something about how important this object is considered to be. This isn't routine, this is a special circumstance where the potential scientific return justified the operational cost. And the return has been substantial. The HiRISE image isn't just a pretty picture, it's a data set. Researchers can measure brightness variations across the Comet and Plume, which tells you about dust density and particle size distribution. They can track the extent of the Plume, which tells you about ejection velocities and how long the material has been travelling. They can compare this image to earlier Hubble images and later ground-based images to see how the Plume is evolving over time. All of that feeds into models that attempt to explain what's happening, and the more data you have, the harder it becomes to force-fit a model that doesn't actually match reality. The HiRISE image, with its clarity and unique perspective, makes it harder to hand-wave away the anomalies. It makes the problem more acute. It forces the question, if this isn't normal comet behaviour, what is it? The Mars vantage point also provided something subtler but equally important: validation. When you see something strange in one telescope, there's always a chance it's an artifact of that telescope's optics or sensors or processing pipeline. Maybe there's a defect. Maybe there's a software bug. Maybe there's some systematic error that's creating a false signal. But when you see the same feature in images from two completely different instruments, observing from two completely different locations, artifact explanations become much less plausible. The HiRISE image and Earth-based observations corroborate each other. They both show Plume activity. They both show the structure extending in a direction that doesn't align with anti-solar expectations. That corroboration strengthens confidence that what we're seeing is real, not an illusion or mistake. So here we are with an image from a camera designed to photograph Martian rocks, pointed at an interstellar visitor millions of kilometers away, capturing details that reveal behavior we can't explain. The Mars Advantage gave us proximity, viewing angle, trajectory refinement, and validation. It gave us a piece of evidence that's harder to dismiss or reinterpret. And now that evidence sits in the dataset, waiting for explanations that can account for it. The question is whether those explanations will come from conventional comet science, or whether we're going to have to think more radically about what 3i Atlas actually is, and that means working through the natural explanations systematically to see if any of them can survive contact with the data. When you encounter data that doesn't fit your expectations, the responsible thing to do is check your explanations, not immediately jump to exotic alternatives. Scientists studying 3i Atlas have done exactly that. They've gone through the list of natural mechanisms that could potentially explain a plume pointing in an unusual direction, and they've tested each one against the observations to see if it holds up. What follows is a graveyard of hypotheses that seemed promising at first but failed under scrutiny. This isn't about proving the object is artificial. This is about honestly assessing whether natural processes can account for what we're seeing, and the uncomfortable conclusion is that they can't, at least not with the mechanisms we currently understand. Let's start with the most obvious explanation: a vent on the nucleus pointing in the direction the plume is extending. Comet nuclei aren't smooth. They have irregular shapes, craters, cliffs, fissures. Sometimes volatilic pockets get exposed in specific locations, creating jets of gas and dust that stream out in directions determined by the local topography. If there's a vent on 3i Atlas that happens to point forward and perpendicular to the Sun, and if that vent is active, you could imagine it producing a localized plume in that direction. That's not crazy. We've seen jets on other comets. But here's where it falls apart. Jets from vents are typically short-lived and highly directional. They produce narrow streams of material that disperse quickly once they get away from the nucleus, because the material doesn't have enough velocity to maintain coherence, and because external forces like radiation pressure and solar wind start redirecting it. The plume in the HiRISE image isn't a narrow jet. It's a broad structure extending over vast distances. For a vent to produce that, the vent would need to be ejecting material at velocities much higher than thermal speeds, and it would need to sustain that ejection over long periods. Thermal sublimation doesn't do that. When ice turns to gas, the gas molecules move at speeds determined by temperature, and for the temperatures you'd expect on a comet at 3i Atlas's solar distance, those speeds are in the range of hundreds of meters per second. That's enough to create a localized jet for a short distance, but it's not enough to sustain a plume extending thousands upon thousands of kilometers unless the material is being ejected continuously at those speeds for days or weeks. And even if you could somehow achieve that, you still have the problem that solar radiation pressure and solar wind would bend the plume toward the anti-solar direction within a relatively short distance from the nucleus. They don't. The plume maintains its perpendicular forward orientation across its entire extent. That requires either no external forces acting on the material, which is impossible because the sun is right there radiating energy and wind, or it requires an internal force continuously counteracting the external forces, which brings you back to the question of what mechanism provides that force. Okay, so maybe it's not a single vent, maybe it's rotation. Comet nuclei spin, and as they spin, different parts of the surface get illuminated by the sun, which means different regions heat up and start sublimating at different times. If the rotation axis is oriented in a particular way, and if the active regions are distributed in a certain pattern, you could get plumes that appear to point in directions other than directly anti-solar, especially if you catch the object at just the right moment in its rotation. That sounds plausible until you work through the numbers. The plume in the high-rise image is large-scale and persistent. It's not a transient feature that appears briefly during one part of the rotation cycle and then vanishes. If it were purely a rotational effect, you'd expect the plume orientation to change noticeably over time as the nucleus rotates and different vents become active or inactive. Observations from multiple epochs don't show that kind of rapid variability. The plume structure is relatively stable, which suggests the mechanism producing it isn't just rotation, exposing different patches of ice to sunlight. There's also the issue of where the energy comes from. Rotation doesn't create energy. It redistributes which parts of the surface receive solar heating, but the total energy input is still determined by the sun. If the plume is pointing perpendicular to the sun, that means it's originating from a region that's not receiving maximum solar flux. The sunward side gets the most energy, the perpendicular side gets less, so you're saying a less heated region is producing a plume that's as prominent or more prominent than what you'd expect from the most heated region. That's backward. That's not how thermal-driven processes work. You don't get more output from less input unless there's another energy source involved, something internal to the nucleus or something else entirely. Let's consider radiation pressure more carefully. Maybe the plume material is being pushed by radiation in a way that's not obvious. Radiation pressure acts on dust particles based on their size and composition. Smaller particles get pushed more strongly. Larger particles get pushed less. If you have a mix of particle sizes, you can get complex plume geometries where different populations of particles spread out in slightly different directions, creating curved or fan-shaped structures. Could that explain what we're seeing? Not really. Radiation pressure always pushes away from the sun. You can get variations in how strongly it pushes, but you can't get radiation pressure pushing material toward a direction perpendicular to the solar direction, or forward along the object's motion. That's just not how photon momentum transfer works. Photons come from the sun, hit particles, transfer momentum in the direction away from the sun. There's no mechanism by which radiation pressure creates a sideways or forward push. What about solar wind? Solar wind is a flow of charged particles, and it interacts with ionized gas in the comet's coma. Could there be some configuration of magnetic fields or plasma dynamics that deflects material into an unusual direction? This is where things get more complicated, because plasma physics in the space environment can produce counterintuitive effects. But even granting that complexity, solar wind fundamentally flows away from the sun. It can drag material, it can create shock structures, it can interact with the comet's induced magnetosphere in interesting ways, but at the end of the day, it's still flowing anti-solar. You're not going to get solar wind creating a sustained forward plume perpendicular to its own flow direction. That violates basic conservation of momentum. The wind can't push material in a direction perpendicular to the direction the wind is moving unless there's something else providing a force in that perpendicular direction. Maybe there's an ice pocket deep in the nucleus that's warmer than the surface, and it's building up pressure until it erupts explosively, shooting material out at high velocity in whatever direction the weak point in the crust happens to face. Explosive outbursts are real. Comets sometimes have them, but they're episodic, not sustained. You get a burst, material flies out, pressure drops, and the activity ceases until pressure builds up again. The plume in the high-rise image doesn't look like the aftermath of a single explosive event. It looks like a sustained flow of material over an extended period. An explosive burst might create a forward-pointing cloud of debris briefly, but that cloud would disperse, It would get acted upon by radiation pressure and solar wind, and within a short time it would lose its forward geometry and shift into the anti-solar configuration that external forces impose. We're not seeing that. We're seeing persistent structure in a direction that external forces should be eliminating. Then there's the possibility of collision. Maybe 3I Atlas hit something, a meteoroid or another comet fragment, and the impact ejected material forward. Impact plumes are a thing. We've seen them in laboratory experiments and in some asteroid observations. But impact plumes are usually asymmetric and chaotic, reflecting the random nature of the collision. They also dissipate quickly. And critically, for an impact to eject material forward along the object's motion, the impactor would need to hit the object from behind, which is statistically unlikely, because objects moving through space at high velocity tend to sweep up material from the front, not get hit from behind. Could it happen? Sure. Is it a plausible explanation for a sustained plume over the time periods we're observing? Not really. Let's talk about composition. Maybe 3I Atlas has unusual volatiles that sublimate at lower temperatures or in different patterns than typical comets. Maybe it's rich in some exotic ice that behaves differently under solar radiation. Maybe the material in the plume has properties that make it immune to radiation pressure or solar wind drag. This is where speculation can run wild, because we don't know the exact composition of 3I Atlas's nucleus. We have spectroscopic data that shows some features, but we don't have complete mineralogical and chemical inventories, so yes, composition could play a role. But even granting that, you still have to explain how unusual composition produces a forward plume. What physical process turns different ice chemistry into forward momentum? Sublimation is sublimation. Ice turns to gas. Gas expands. The thermal velocity is determined by temperature, not by which specific molecule is doing the sublimating. Different volatiles have different sublimation temperatures and different molecular masses, which affects thermal velocity somewhat. But none of that creates a mechanism for sustained forward ejection perpendicular to the Sun. Here's the fundamental problem that all these natural explanations run into. They're trying to explain a directional effect, a plume pointing in a specific direction, using mechanisms that are either non-directional, like thermal expansion, or directional in the wrong way, like radiation pressure pushing anti-solar. You can stack mechanisms on top of each other. You can say maybe it's rotation plus an active vent, plus unusual volatiles, plus a weird viewing angle. But stacking doesn't solve the core issue. At some point you need a force pushing material forward and perpendicular to the Sun, and none of the natural mechanisms provide that force. Sublimation provides outward expansion from the nucleus. Radiation pressure provides anti-solar push. Solar wind provides anti-solar drag. Gravity provides inward pull toward massive bodies. Rotation provides time-varying orientation. None of those, individually or in combination, give you sustained forward perpendicular motion at the scales we're observing. A.V. Loeb's point in raising the technological hypothesis isn't that technology is the only explanation, or even the most likely explanation. It's that natural explanations have been tried and they don't fit, and therefore we need to expand the hypothesis space to include possibilities we might not have considered, because they're uncomfortable or unconventional. If you're doing science correctly, you follow the evidence. The evidence says plume in the wrong direction. The evidence says natural mechanisms don't account for it. The evidence therefore invites you to consider what else might account for it, even if that else is something you'd prefer not to think about because it opens up implications that are difficult to process. This is where we are. Natural explanations have been tested against the data and found insufficient. That doesn't mean they're impossible. It means they require conditions or mechanisms we haven't identified yet, and those conditions would need to be specific enough and unusual enough that we've never seen them in any other comet despite decades of observations. You can believe that 3I Atlas is just the first example of a whole class of comets that behave this way, and we've been unlucky not to see one before. Or you can entertain the possibility that it's not a comet, that it's something else wearing a comet's disguise, and the plume is a clue that the disguise isn't perfect. Either way, the natural explanations we know don't fit, and that gap is where the mystery lives right now. The question then becomes, if not natural, what? What technological mechanism could produce a plume like this, and why would such a mechanism exist? That's speculative territory, but it's speculation grounded in the failure of conventional explanations, which makes it worth exploring carefully. This is the part where things get uncomfortable, not because the science is complicated, but because the implications are. When you've ruled out natural explanations and you're left staring at data that doesn't fit, you have to ask the question that most scientists would rather not ask in public. Could this be artificial? Could we be looking at technology? And before you dismiss that as fringe speculation or attention-seeking sensationalism, understand that asking the question isn't the same as claiming the answer. It's intellectual honesty. It's the scientific method applied to a genuinely anomalous observation. You don't ignore data because it makes you uncomfortable. You interrogate it. You explore hypotheses. You test them. And if one of those hypotheses involves technology, you consider it alongside everything else. Avi Loeb has built a career on asking uncomfortable questions. He was the one who proposed that Oumuamua, the first confirmed interstellar object detected in our solar system back in 2017, might be artificial based on its unusual acceleration and elongated shape. That proposal was met with significant pushback from the astronomy community, not because the data was wrong, but because the interpretation challenged deeply held assumptions about what kinds of objects travel through interstellar space. Loeb's argument wasn't that Oumuamua definitely was artificial, it was that the hypothesis of artificiality fit the data better than purely natural explanations, and therefore deserved serious consideration. The same logic applies to 3i Atlas. The Plume geometry doesn't fit natural mechanisms. Technological mechanisms could fit. Therefore, explore technological mechanisms as a hypothesis and see where it leads. So let's explore. What technological scenario could produce a plume pointing forward and perpendicular to the Sun? One possibility is a debris clearing system. Imagine you're travelling through interstellar space at high velocity, tens of kilometers per second. At those speeds, even tiny particles can cause damage if they hit sensitive components. A grain of dust travelling at 10 or 20 kilometers per second relative to your spacecraft has enormous kinetic energy. It's a micrometeorite impact, and enough of them could erode surfaces, puncture shielding, damage instruments. If you're on a long interstellar journey, protection from micrometeoritic impacts becomes a serious design consideration. One way to protect is passive shielding, thick armor that absorbs impacts. Another way is active clearing, ejecting material ahead of your trajectory to sweep space in front of you, either vaporizing incoming particles through collisions or deflecting them out of your path. A forward-pointing plume would make sense for active clearing. You're not trying to propel yourself. You're trying to modify the environment ahead of you. You eject material, maybe gas, maybe small particles, in the direction you're traveling. That material spreads out, creating a diffuse cloud ahead of the main body. Anything moving toward you through space hits that cloud first. Collisions with the cloud particles transfer momentum, slow down the incoming debris, maybe vaporize it if the collision energy is high enough. The cloud acts as a shield, a buffer zone that protects the main structure from direct high-velocity impacts. If you're doing this continuously as you travel, you'd expect to see a sustained plume ahead of the object, exactly like what the high-rise image shows. Why perpendicular to the Sun? Maybe because the clearing mechanism is optimized for the direction of motion, not for solar considerations. If you're traveling through interstellar space, the Sun is just one star among many. Your trajectory isn't dictated by the Sun. You're on a path determined by your origin and destination, and the Sun happens to be a gravitational obstacle you're navigating around. The direction you need to clear is ahead of you along your velocity vector, regardless of where the Sun is. So the plume points forward, because that's where the threat is, and it points perpendicular to the Sun because your trajectory happens to be oriented that way relative to the solar system's geometry. It's not that the Sun doesn't matter. It's that the Sun isn't the primary consideration for a system designed to operate in interstellar space where solar influence is weak or absent. Another technological scenario is propulsion. If 3i Atlas is accelerating, or adjusting its trajectory, or maintaining velocity against drag forces, it would need to expel reaction mass. That's basic rocket physics. You throw mass in one direction, you get thrust in the opposite direction. If the plume is material being ejected as reaction mass, the direction of the plume tells you the direction of thrust, which is opposite the direction of acceleration. A forward-pointing plume would imply the object is decelerating, slowing down along its trajectory. Why would it be decelerating? Maybe it's preparing for some kind of maneuver, maybe it's reducing speed to adjust its path through the solar system. Maybe the trajectory we're observing isn't a natural hyperbolic orbit determined purely by gravitational interactions, but a controlled path where the object is actively managing its velocity and direction. There's precedent for this kind of thinking with Oumuamua. Oumuamua exhibited a small but measurable non-gravitational acceleration as it left the solar system. That acceleration couldn't be explained by outgassing, which was the standard natural explanation for non-gravitational forces on comets, because Oumuamua showed no signs of a coma or tail, no visible outgassing. Yet it was accelerating. Loeb proposed that the acceleration could be explained by radiation pressure if Oumuamua was a thin light sail, a large flat reflective surface being pushed by solar photons. That's a technological explanation. A light sail is a piece of technology designed to use radiation pressure for propulsion. Critics argued for natural explanations involving exotic outgassing of hydrogen or other mechanisms, but those explanations required assumptions that strained plausibility. The point is, when you see non-gravitational acceleration and no obvious natural mechanism, technology becomes a viable hypothesis. With 3i Atlas, we're not necessarily seeing anomalous acceleration, but we are seeing a plume that implies mass ejection in a specific direction. Mass ejection generates force. Force changes velocity. If the plume is sustained, the force is sustained, and you'd expect measurable trajectory changes. Researchers are looking for exactly that. They're analysing the object's orbit to see if there are any deviations from what you'd predict based purely on gravity. If there are deviations, and if those deviations align with the plume direction, that would strengthen the case that the plume represents active propulsion rather than passive outgassing. Let's think about what it would mean if 3i Atlas were artificial. First, it would mean something built this object and sent it on an interstellar journey, that something could be another civilization, or it could be us in some far future scenario where we've developed interstellar travel, and this is a probe we sent that's now returning through our solar system, though the timing and trajectory make that unlikely. It would mean the object has technology capable of surviving the harsh environment of interstellar space for potentially millions or billions of years, because interstellar travel at non-relativistic speeds takes an extremely long time. It would mean the object either still has active systems functioning after all that time, or it has automated systems that activate under certain conditions, like proximity to a star. It would mean we're not alone. That's the big one. That's the implication that makes this hypothesis uncomfortable. Detecting artificial technology from another civilization would be the most profound discovery in human history, and it's the kind of discovery that scientists are trained to be extremely skeptical about, because the consequences of being wrong are severe. But skepticism doesn't mean dismissal. Skepticism means demanding rigorous evidence before accepting extraordinary claims. The claim that 3i Atlas might be artificial is extraordinary. The evidence so far, the plume geometry, and the failure of natural explanations is intriguing but not definitive. It's enough to warrant the hypothesis. It's not enough to confirm it. Confirmation would require additional data showing features that can't plausibly be natural. For example, if spectroscopy revealed industrial chemicals or refined metals in the plume composition, if thermal imaging showed heat signatures inconsistent with solar heating, if high-resolution imaging resolved geometric structures on the nucleus, shapes that are too regular or organized to be natural, if radio observations detected signals or electromagnetic emissions that imply technology. None of that has been found yet. What we have is a plume pointing the wrong direction. That's the seed of the hypothesis, not the proof. Loeb's approach to this is methodical. He's not saying trust me, it's aliens. He's saying here's an observation that doesn't fit natural models, here's a technological hypothesis that could fit, let's gather more data to test the hypothesis. That's science. That's how you're supposed to handle anomalies. You don't force-fit a natural explanation that doesn't work just because natural explanations are more comfortable. You don't jump to extraordinary conclusions without evidence. You hold multiple hypotheses in mind simultaneously, evaluate them against data, and follow where the evidence leads. Right now, the evidence leads to a question mark. A big one. A question mark that's shaped like a plume pointing in an impossible direction. Think about the challenges of interstellar travel from an engineering perspective. If you wanted to send a probe to another star system, you'd need to solve enormous problems. Propulsion to accelerate the probe to speeds where the journey doesn't take millions of years. Shielding to protect it from radiation and micrometeorite impacts during the journey. Power to keep systems running for centuries or millennia. Navigation to stay on course across light years of space. Communication to send data back. though at interstellar distances signal lag becomes prohibitive, and hardening to ensure components survive the thermal, mechanical and radiation stresses of the journey. Every one of those problems has solutions in principle, but the engineering is daunting. If another civilization solved those problems and built interstellar probes, what would we expect them to look like? One strategy would be camouflage. If you're entering an unknown star system, you don't necessarily want to advertise your artificial nature immediately. You might want to observe quietly, blend in, avoid triggering defensive reactions from any civilizations that might be present. A probe disguised as a comet or asteroid would blend in perfectly. It would look like countless other natural objects moving through the system. It would avoid attention, and if it needed to do anything active like adjust its trajectory or clear debris, it might produce side effects that look unusual, like a plume pointing the wrong direction, but those side effects might not be obvious unless someone looks closely. That's speculative, but it's not absurd. It's a rational design choice if your goal is covert observation. Another consideration is longevity. An interstellar probe might not have active systems running continuously. It might be in a dormant state for most of the journey, conserving power, minimizing wear. Then when it approaches a star, sensors detect the increased radiation, systems wake up, the probe activates whatever instruments or mechanisms it was designed to deploy in a stellar environment. If 3i Atlas is something like that, the Plume might represent initial activation, systems coming online, testing propulsion, or clearing mechanisms after a long dormancy. The timing fits. The Plume activity became noticeable around the time 3i Atlas was near the Sun, which is when you'd expect a dormant probe to wake up and start doing whatever it was sent to do. Of course, all of this is speculation built on a foundation of one anomalous observation. That's important to emphasize. We're not at the point where we can say with confidence that this is technology. We're at the point where we can say natural explanations are insufficient and technological explanations are worth considering and testing. The difference matters. Speculation is fine as long as it's labelled as speculation, and as long as it's accompanied by proposals for how to test it. Loeb isn't just throwing out the technological hypothesis and walking away. He's advocating for more observations, better data, targeted studies that can distinguish between natural and artificial origins. He's saying let's find out, not let's assume. And here's the thing, even if 3i Atlas turns out to be entirely natural, even if we eventually discover some exotic comet process that explains the Plume geometry perfectly, the fact that we had to seriously consider technological hypotheses tells you something important about where we are as a species. We're at the point where detecting interstellar objects is routine. We have the instruments. We have the observational networks. We're going to keep finding these things as telescope technology improves, and some of them are going to be weird. Some of them are going to show behaviors we don't immediately understand. We need a framework for evaluating those behaviors, and that framework has to include the possibility that some of them might be artificial. Not because we want to find aliens, because if artificial objects are out there, we need to be able to recognize them when we see them. That requires asking the uncomfortable questions. That requires entertaining hypotheses that feel strange. That requires following evidence even when it points toward conclusions that challenge our place in the universe. So the technological question isn't about proving 3i Atlas is a probe. It's about being honest that the data invites that possibility and being rigorous in how we test it. It's about not letting our discomfort with the implications prevent us from doing the science. And it's about recognizing that whether the answer turns out to be natural or artificial, we're learning something profound about the universe and our ability to understand it. The Plume points forward. The question is why? And the answer, whatever it is coming. The answer is coming because we're not done observing 3i Atlas, and the next phase of observations is going to give us the data we need to resolve this mystery one way or another. The beauty of science is that it doesn't leave you hanging indefinitely. When you have a mystery, you design observations to solve it. When you have competing hypotheses, you gather data that can distinguish between them. 3i Atlas is still out there, still observable, still within range of our most powerful telescopes, and in the coming weeks those telescopes are going to be pointed at this object with one goal: figure out what's causing that plume. The observations that are planned and already in progress aren't casual. They're targeted, strategic, designed to extract specific information that can tell us whether we're looking at exotic natural processes or something else entirely. Let's start with spectroscopy, because composition is key. When light from the sun reflects off the plume material, or when the material itself emits light due to fluorescence or thermal radiation, that light carries information about what the material is made of. Different molecules and atoms absorb and emit light at specific wavelengths, creating spectral signatures that act like fingerprints. Water vapor has a fingerprint. Carbon monoxide has a fingerprint. Organic compounds have fingerprints. Metals have fingerprints. By analysing the spectrum of light coming from the plume, astronomers can identify which substances are present and in what relative abundances. That tells you whether you're looking at typical comet volatiles, water ice and carbon compounds, or something unusual, industrial chemicals, refined metals, materials that don't occur naturally in cometary environments. Hubble Space Telescope has already conducted some spectroscopic observations of 3I Atlas earlier in its trajectory, and those observations revealed interesting things. The object showed strong carbon dioxide signatures, stronger than typical comets. It also showed some nickel and iron emission lines, which was surprising because while comets contain metals, you don't usually see them in emission at the levels that were detected. Those early spectra hinted that 3I Atlas wasn't a typical comet, but they didn't provide enough detail to say definitively what it was. Now, with the plume clearly visible and extended, Hubble is conducting follow-up spectroscopy, focused specifically on the plume material. What volatiles are in the plume? What dust composition? Are there any unexpected elements or molecules that shouldn't be there if this is just ice sublimating naturally? James Webb Space Telescope is also being brought into play. Webb operates in the infrared, which is perfect for studying cold objects in space, and for detecting specific molecules that have strong infrared signatures. Carbon dioxide, methane, water ice, all of these show up beautifully in infrared spectroscopy. Webb's sensitivity is unmatched. It can detect faint signals that other telescopes miss. If there's something unusual in the plume's composition, something present in small quantities that's being overwhelmed by the dominant components in visible light observations, Webb should be able to pick it out. The infrared also lets you measure thermal properties. How warm is the plume material? How does temperature vary across the plume? That tells you about energy sources. If the material is warmer than it should be based on solar heating alone, that implies an internal energy source, something generating heat from within the nucleus. Ground-based telescopes are joining the effort as well. Large observatories with advanced spectrographs and adaptive optics systems can track 3I Atlas as it moves through the sky and gather high-resolution data over extended periods. The advantage of ground-based observations is time. You can watch the object night after night, monitoring how the plume evolves, whether it brightens or fades, whether its geometry changes, whether new structures appear. Hubble and Webb have limited observing time. They're shared resources with packed schedules. Ground-based telescopes can dedicate more continuous attention to a single target if the science justifies it, and right now, the science absolutely justifies it. One of the critical measurements being pursued is the mass loading rate of the plume. That's a fancy term for how much material is being ejected per unit time. If you can measure the density of dust and gas in the plume, and the velocity at which it's moving away from the nucleus, you can calculate how many kilograms per second are being thrown off. That number tells you about the energy budget, how much energy is required to sublimate that much ice and accelerate that much material. Compare that to the solar energy hitting the nucleus, and you can see whether solar heating alone is sufficient or whether you need an additional energy source. If the mass loading rate is higher than solar heating can account for, that's a big clue that something else is driving the activity. Velocity measurements are also crucial. How fast is the plume material moving? If it's moving at thermal speeds a few hundred meters per second, that's consistent with sublimation-driven expansion. If it's moving faster, significantly faster, that implies the material has been accelerated by something beyond thermal pressure. Acceleration requires force. Force requires energy. High-velocity plumes require mechanisms that can deliver energy to the material efficiently. And natural sublimation isn't particularly efficient at producing high-speed ejecta. So velocity measurements can help distinguish between passive outgassing and active propulsion, or clearing mechanisms. Then there's the question of how the plume changes over time. Is it persistent, maintaining the same orientation and intensity over days and weeks? Or is it variable, flickering on and off, changing direction as the nucleus rotates or as solar conditions change? Persistence suggests a steady-state process, something that's either continuously powered or continuously driven by the object's motion through space. Variability suggests a more sporadic process, may be related to specific active regions on the nucleus being illuminated at certain times. Observing campaigns are designed to catch the object at multiple points in its orbit, building up a time-lapse view of how the plume behaves as circumstances change. Radio observations are another tool in the arsenal. Radio telescopes can detect emissions from molecules like carbon monoxide and hydrogen cyanide, which are common in comets. They can also detect any electromagnetic signals that might be artificial in origin, though that's a long shot. The primary value of radio observations is measuring the production rates of specific gases and mapping their distribution around the nucleus. Gas production rates correlate with activity levels. If the rates are consistent with solar-driven sublimation, that supports natural explanations. If they're inconsistent, that's another piece of evidence that something unusual is happening. Polarimetry is a more specialized technique that measures how light is polarized when it reflects off dust particles in the Comet and Plume. The degree and angle of polarization depend on particle size, shape, and composition. Polarimetric observations of 3I Atlas earlier in its trajectory showed unusual polarization properties, different from typical comets. That was another hint that the dust in this object's environment isn't standard comet dust. Follow-up polarimetry of the Plume can refine that finding, determining whether the plume dust has the same unusual properties or whether it's different, which might indicate a different source region or formation mechanism. High-resolution imaging is ongoing as well. Every time a capable telescope gets a chance to photograph 3I Atlas, researchers are looking for structural details on the nucleus. Is it a single solid body or a cluster of fragments? Are there visible surface features, bright or dark patches, jets, vents? Is the nucleus symmetric or irregular? Does it rotate, and if so, what's the rotation period? All of these details feed into models of how the object formed and how it's behaving now. If the nucleus has artificial features, geometric shapes, surface patterns that look designed rather than random, that would be detectable in sufficiently high-resolution images. We're not there yet. The nucleus is too small and too distant for current telescopes to resolve fine details. But as 3I Atlas's trajectory continues, opportunities for closer views might arise, or future missions might target it specifically if the evidence becomes compelling enough. There's also the possibility of detecting changes in the object's trajectory that aren't explained by gravity alone. Astrometric observations, precise measurements of the object's position over time, can reveal tiny accelerations. If the plume is generating thrust, that thrust would show up as a deviation from the purely gravitational orbit. Researchers are combing through positional data looking for exactly that. It's delicate work because the accelerations, if they exist, are small, and you have to account for gravitational perturbations from planets and even distant stars. But it's doable, and it's being done. If non-gravitational acceleration is confirmed and it correlates with the plume direction, that would be strong evidence for active propulsion. What makes this moment so exciting is that these observations aren't hypothetical. They're happening right now. Telescopes are tracking 3I Atlas. Data is being collected. Researchers are analysing spectra, measuring velocities, tracking changes. Within weeks, we're going to have a much more complete picture of what this object is and what's causing the plume. Maybe the new data will reveal a natural explanation that fits perfectly, some combination of factors that we overlooked or didn't model correctly. Maybe the data will deepen the mystery, adding more anomalies that make natural explanations even less tenable. Or maybe the data will provide clear evidence of artificiality, signatures that can't be explained away, that demand we confront the reality that we're looking at technology. Any of those outcomes would be scientifically valuable. Finding a natural explanation for the plume would expand our understanding of comet physics and interstellar object behavior. It would teach us that nature is more diverse and creative than we realized. Deepening the mystery would drive further investigation, more sophisticated observations, better models. It would push the boundaries of our observational and theoretical capabilities. And finding evidence of technology, well, that would change everything. It would confirm that we're not alone. It would provide a target for follow-up studies, maybe even future missions. It would force us to rethink our place in the cosmos and the likelihood that intelligence is common or rare in the universe. The timeline for these observations is compressed because 3I Atlas is moving away from the Sun, and as it gets farther out, it becomes fainter and harder to observe. There's a window, maybe a few months, where we can still gather high-quality data before the object fades into the background and becomes too dim for all but the most powerful telescopes. That urgency is driving the coordination of observing campaigns across multiple facilities. Everyone wants a piece of this. Everyone wants to contribute to solving the mystery, and that collective effort, that mobilization of resources and expertise, is itself a testament to how significant this object has become in the eyes of the scientific community. So the answer is coming. Whether it's the answer anyone expects is another question. Science has a way of surprising you. Data doesn't care about your assumptions or your preferences. It just is. And whatever the data from these upcoming observations reveals, we're going to have to accept it and adjust our understanding accordingly. The plume is there, the direction is wrong, the explanations are insufficient, the observations will tell us why. And in the meantime, we wait and we watch, and we wonder what we're actually seeing up there in the darkness between worlds. Before we get to the conclusion, it's worth stepping back and looking at the bigger picture, because 3i Atlas isn't just one weird object, it's part of a growing category of interstellar visitors, and understanding that context helps us appreciate what this moment might mean for the future. 3i Atlas is the third confirmed interstellar object we've detected passing through our solar system. Third, in less than a decade we've gone from 0 confirmed interstellar visitors to 3, and that's probably not because interstellar objects suddenly started showing up in the last few years. It's because our detection capabilities improved. We built better telescopes. We developed automated survey systems that scan the sky continuously looking for anything that moves. We created databases and algorithms that flag unusual trajectories, objects moving too fast or in the wrong direction to be bound to the sun. We got good at spotting needles in the cosmic haystack, and now that we're looking, we're finding them. Oumuamua was the first, detected in 2017. It was bizarre from the start. Extremely elongated shape, tumbling rotation, reddish colour suggesting surface organics, and that unexplained non-gravitational acceleration as it left the solar system. It didn't look like a comet. It had no visible coma or tail, but it was accelerating in a way that suggested outgassing, except there was no gas. Natural explanations were proposed: hydrogen icebergs, nitrogen icebergs, dust-covered volatiles releasing material invisibly. Technological explanations were proposed: light sails, debris from alien technology, probes. None of the explanations were entirely satisfying. Oumuamua left more questions than answers, and by the time we realized how weird it was already too far away for detailed follow-up observations. We missed our chance. All we have are the handful of images and spectra collected during its brief passage through the inner solar system, and those data points aren't enough to settle the debate about what it was. The second interstellar object, 2I Borisov, was detected in 2019. It looked like a normal comet. It had a coma. It had a tail. It outgassed in ways consistent with solar-driven sublimation. Spectroscopy showed familiar molecules: carbon monoxide, water. Its orbit was hyperbolic, proving it came from interstellar space, but its behavior was boringly conventional. 2I Borisov was a relief in some ways because it showed that not all interstellar objects are mysterious. Some of them are exactly what you'd expect: comets ejected from other star systems travelling through the galaxy, until they happen to pass close enough to our sun to light up and become visible. Borisov was normal, and normal was comforting after the strangeness of Oumuamua. Now we have 3i Atlas, and it's somewhere in between. It has comet-like features, a coma, a plume, activity that correlates with solar proximity. But it also has anomalies: the plume direction, the unusual composition revealed in early spectroscopy, the polarization properties that don't match typical comets, the persistent activity in regions that shouldn't be producing much outgassing based on solar illumination. It's not as overtly weird as Oumuamua, but it's not as reassuringly normal as Borisov. It's ambiguous, and ambiguity is unsettling because it means you can't easily categorize it and move on. You have to sit with the uncertainty and keep probing until the picture clarifies. Here's what 3 interstellar detections in less than a decade tells you. These objects are not rare. There are probably millions or billions of interstellar objects passing through the solar system at any given time, most of them too small or too far away to detect. The ones we've found so far are the lucky ones, the ones that passed close enough to the sun or Earth to light up or be spotted by our surveys. As telescope technology continues improving, especially with next-generation survey systems coming online in the next few years, we're going to detect interstellar objects regularly, maybe dozens per year, maybe more. We're going to build up a catalogue, a statistical sample, and that sample will tell us what's typical and what's unusual in the population of objects travelling between the stars. And here's the critical question. What percentage of those objects are natural, and what percentage might be artificial? Right now, we don't know. We have 3 data points, one ambiguous, one normal, one ambiguous in a different way. That's not enough to draw statistical conclusions, but it's enough to establish that the question is worth asking. If interstellar objects are common, and if even a small fraction of them are artificial probes sent by other civilizations, then we should be detecting those probes as our survey capabilities improve. Finding them requires knowing what to look for, which means we need criteria for distinguishing natural from artificial. That's not trivial. Nature is weird. Nature produces shapes and behaviors that can look designed. And conversely, artificial objects designed for interstellar travel might mimic natural objects to avoid detection, or simply because comet-like bodies are convenient forms for shielding and resource transport. The scientific community is starting to grapple with this. There are now serious discussions about how to approach the search for interstellar artifacts, what signatures to look for, how to avoid false positives where natural objects get misidentified as artificial, and how to avoid false negatives where artificial objects get dismissed as natural. The Galileo project, led by Avi Loeb, is one effort focused specifically on this. The project aims to design and deploy instruments capable of detecting and characterizing anomalous objects in near-Earth space and in the solar system more broadly. The idea is to take the search for technosignatures seriously, not as a fringe activity but as a legitimate scientific endeavor with rigorous methodology. Part of what makes this conversation difficult is the stigma. For decades, talking about aliens in the context of professional astronomy was career suicide. It was associated with UFO enthusiasts and conspiracy theorists, not serious scientists. That stigma has been damaging because it discourages people from asking legitimate questions about whether we're alone and whether we'd recognize evidence of other intelligences if we saw it. The stigma is starting to fade, partly because of high-profile cases like Oumuamua, where the data genuinely doesn't fit easy natural explanations, and partly because of institutional changes like NASA, establishing a formal office for studying unidentified aerial phenomena, and the broader acceptance that the search for extraterrestrial intelligence is a valid scientific pursuit. But the stigma still exists, and it still influences how researchers approach ambiguous data. 3i Atlas sits right at that intersection of ambiguity and stigma. The data is strange enough to warrant consideration of non-natural explanations, but not strange enough to force that conclusion. Researchers studying it have to navigate carefully. Push too hard on the artificial hypothesis without sufficient evidence, and you risk being labelled a crank. Ignore the artificial hypothesis and force-fit natural explanations that don't quite work, and you risk missing something genuinely historic. The balance is delicate, and the stakes are enormous. Let's think about what it would mean to find even one confirmed artificial object in our solar system. It would mean that interstellar travel is achievable, that some civilization somewhere figured out how to build probes that can survive the journey between stars. It would mean that such probes might be common, that maybe every advanced civilization sends them out as a way to explore the galaxy, or communicate with others. It would mean we're embedded in a network of intelligence that spans the galaxy, even if direct communication is impossible due to the vast distances and time lags involved. It would fundamentally change our understanding of our place in the universe. We'd go from alone to one among many, from unique to typical, from the centre of our own story to a chapter in a much larger narrative. But it would also raise uncomfortable questions. If there are probes in our solar system, what are they doing? Are they observing us? Have they been here longer than we've been aware of them? Are they passive instruments collecting data, or do they have active capabilities? If we detect one, should we try to interact with it, or is that dangerous? Do we have protocols for handling first contact with an artifact as opposed to first contact with a living being? These aren't hypothetical questions anymore. They're questions we might need answers to in the near future if objects like 3i Atlas turn out to be more than they appear. The bigger picture also includes the evolution of our observational capabilities. We're living through a golden age of astronomy. Telescopes in space and on the ground are more powerful than ever. Data processing algorithms can sift through millions of images to find anomalies. International collaboration means observations from multiple sites can be coordinated to track objects continuously. and the pace of improvement is accelerating. The Vera Rubin Observatory, set to begin operation soon, will survey the entire visible sky every few nights, detecting anything that changes or moves. It will find thousands of asteroids, comets, and transient events. And among those thousands, it will find more interstellar objects. Many more. Within a decade, we'll have a robust sample of interstellar visitors, and that sample will answer questions we can't answer with just 3 examples. One of those questions is compositional diversity. Are interstellar objects made of the same materials as solar system comets and asteroids, suggesting universal processes of planetary system formation? Or do they show exotic compositions, materials or isotopic ratios that indicate formation in environments very different from our solar system? Another question is behavioral diversity. Do most interstellar objects follow predictable orbits and exhibit typical comet or asteroid behavior, or are there common anomalies, unusual accelerations, unexpected outgassing, plumes in wrong directions? If anomalies are rare, then objects like Oumuamua and 3I Atlas are outliers, and maybe natural explanations will eventually be found. If anomalies are common, that might suggest something systematic is going on, maybe a whole class of objects with properties we don't understand yet. There's also the question of origin. Where do interstellar objects come from? Some are probably natural ejecta from planetary systems, comets or asteroids thrown out by gravitational interactions with planets and sent wandering through the galaxy. Some might be remnants of stars that died, material blown off in supernovae or planetary nebulae that coalesced into small bodies and drifted through space. And some, maybe, are artificial, probes built and launched by civilizations interested in exploring beyond their home systems. Distinguishing between these origins requires detailed characterization, which is why follow-up observations of objects like 3I Atlas are so critical. Every piece of data helps refine the origin story. Understanding the bigger picture also means recognizing that we're building the foundation for future research. Every interstellar object we study teaches us something. Even if 3I Atlas turns out to be entirely natural, the effort to understand it advances our knowledge of comet physics, interstellar environment effects on small bodies, and observational techniques for faint distant targets. And if it turns out to be artificial, well, that advances everything. It opens entirely new fields of study. Astroarchaeology, the study of ancient or alien artifacts, interstellar probe design and detection, the sociology and strategy of civilizations that build such probes. We're not just looking at 3I Atlas, we're looking at the future of discovery, and that future is beginning now, one strange plume at a time. So as we watch the data come in from Hubble and Webb and ground-based telescopes, as we read the papers and follow the debates about what this object is, remember that this is bigger than one comet or one hypothesis. This is about humanity learning to see the universe as it actually is, not as we assumed it was. It's about expanding our categories, questioning our assumptions, and being willing to follow evidence into territory that feels alien and uncertain. That's where discovery lives. That's where the answers are. And the fact that we're uncomfortable getting there is a sign we're doing it right. Because comfort comes from staying in familiar territory, and familiar territory doesn't teach you anything new. Which brings us finally to the conclusion, where we have to sit with the uncertainty and ask what it means to live in a moment where we don't yet have answers, but we know we're close to getting them. Here's the truth. We don't know what 3I Atlas is. Not yet. We have data that doesn't fit expectations. We have hypotheses, some conventional, some radical. We have observations in progress that will give us more information in the coming weeks, but right now, in this moment, we're living with uncertainty. And that's okay. That's actually how science works most of the time. You encounter something you don't understand, you probe it, you gather data, you test explanations, and gradually the picture comes into focus. Sometimes the process is quick. Sometimes it takes years or decades. But the process works, and eventually reality reveals itself. What we know definitively about 3I Atlas is this. It's an interstellar object, confirmed by its hyperbolic trajectory, that proves it came from beyond our solar system. It exhibits comet-like activity, outgassing that creates a visible coma and plume. The plume orientation as seen in the high-rise image from Mars Reconnaissance Orbiter is anomalous, pointing in a direction that doesn't align with conventional models of how solar radiation and solar wind should affect cometary material. Natural explanations involving vents, rotation, Unusual volatiles and exotic nucleus properties have been considered and found insufficient based on current data. Technological explanations involving debris clearing or propulsion have been proposed as hypotheses worth exploring, not as confirmed facts. Upcoming observations from Hubble, James Webb, and ground-based telescopes will provide compositional, thermal, and dynamical data that can test these hypotheses and potentially resolve the mystery. That's what we know. Everything beyond that is speculation, informed speculation in some cases, wild speculation in others, but speculation nonetheless. The plume might be natural and we just haven't figured out the mechanism yet. The plume might be technological, and we're on the verge of confirming the first artificial interstellar object ever detected. The plume might be something in between, some exotic natural process that involves physics or chemistry we haven't fully understood in astrophysical contexts. We won't know until the data comes in and gets analysed, and even then, there might not be immediate consensus. Scientists will argue. They'll propose different interpretations. They'll demand more observations. That's healthy. That's how you avoid jumping to conclusions based on incomplete information. What's important is that we're asking the questions. We're not dismissing the anomaly because it's inconvenient. We're not forcing an explanation because it makes us comfortable. We're taking the data seriously and following it where it leads, even when that path is uncomfortable, even when it raises possibilities that challenge our assumptions about what exists in the universe and whether we're alone in it. That willingness to question, to explore, to sit with uncertainty without prematurely closing the inquiry, that's the essence of intellectual honesty. That's the difference between dogma and discovery. Think about what this moment represents. We're living in an era where detecting interstellar visitors is routine, where we can photograph them from Mars, analyse their composition with space telescopes, and debate their nature in real time as data arrives. 100 years ago, we barely understood that other galaxies existed. 50 years ago, we didn't know if planets around other stars were common. 20 years ago, we'd never detected an interstellar object. Now we're on our third, and we're seriously discussing whether one of them might be artificial. The pace of change is staggering. The expansion of what we know and what we can observe is accelerating. And with that acceleration comes the increasing likelihood that we're going to encounter things that don't fit neatly into our existing frameworks. Things that force us to expand those frameworks or build new ones. 3i Atlas is one of those things. Whether it's ultimately explained naturally or not, it's pushed us to think harder about what's possible, what's plausible, and what evidence would be required to confirm extraordinary hypotheses. That's valuable even if the object itself turns out to be ordinary once we understand it better. The process of grappling with the unknown strengthens our methods and sharpens our thinking. It prepares us for the next anomaly, and the one after that, because there will always be a next anomaly. The universe is stranger and more diverse than any model can fully capture, and every time we think we've got it figured out, something new shows up to remind us how much we still have to learn. So where does that leave us? It leaves us watching, waiting, hoping for clarity but prepared for ambiguity. It leaves us engaged in one of the most exciting scientific investigations of our time, a real-time mystery unfolding with observational campaigns and data analysis happening as we speak. It leaves us connected to something larger than our individual lives, a collective human effort to understand the cosmos and our place in it. And it leaves us humble, because if 3i Atlas teaches us anything, it's that we don't have all the answers, and that's okay, because the pursuit of answers is what drives us forward. In a few weeks we'll know more. Maybe we'll have spectroscopic confirmation that the plume is made of ordinary comet volatiles, and someone will propose a clever natural mechanism that explains the geometry. Maybe we'll have thermal data showing internal heat sources that can't be solar. Maybe we'll have trajectory analysis revealing non-gravitational acceleration consistent with propulsion. Maybe we'll have images showing structure on the nucleus that looks designed. Or maybe we'll have more ambiguity, more data that's intriguing but not definitive, and the mystery will deepen before it resolves. Any of those outcomes is possible, and all of them move us closer to understanding. What we shouldn't do is stop asking questions. What we shouldn't do is let discomfort with certain possibilities prevent us from exploring them rigorously. What we shouldn't do is assume we already know the answer before the evidence is complete. The plume is there, the direction is wrong, the explanations are incomplete. That's the reality, and reality doesn't care what we believe or what we're comfortable with. It just is. Our job is to observe it, measure it, test our ideas against it, and adjust our understanding when the data demands it. That's science. That's discovery. That's how we learn. So I'm asking you, what do you think? Have you been following 3i Atlas? Did you know about this Plume anomaly before now? Does it change how you think about what's out there in the space between stars? Are you comfortable with the idea that we might be looking at technology, or does that feel too far-fetched given the evidence we have so far? Drop your thoughts in the comments. Tell me if you think there's a natural explanation we're missing. Tell me if you think Loeb is onto something. Tell me if you're excited or skeptical or somewhere in between. This is a conversation worth having, a moment worth paying attention to, because whatever 3i Atlas turns out to be, the fact that we're here, asking these questions, analysing these images, testing these hypotheses, that's a sign of how far we've come and how much further we're about to go. The universe is full of mysteries. This is one of them, and it's ours to solve.